Okay, example 3, our transfer function here, the component is 1 over s, so that represents an integrator in the Laplace domain. If we want to find the frequency response function for this, for harmonic input, we evaluate s at j omega just as before, so it's 1 over j omega. The modulus of that's just 1 over omega. In dB form, well, we take the log of g multiplied by a 20. And so keep in mind that when this is the log of omega to the minus 1 power, and log of omega to the minus 1 power brings a minus sign there on the outside. The phase angle is the inverse tan of the imaginary part, which is going to be a minus j over omega, and that's divided by the real part, which is a 0. So I've actually got a mistake here. This is written as that, but the result is the same. The phase angle is minus 90 degrees for all omega. So in this case, we see that the exact is the same thing as a linear approximation, because we see what this is. This is something that represents a straight line in dB world with a minus 20 dB per decade change. So as you increase omega, the amplitude goes down. It goes down at a rate in dB of 20 dB per decade. So I didn't give us a plot here, but if I had, if I'm plotting omega and the magnitude of this in dB, what we would have is 0 dB. The omega, when omega is equal to 1, we see that that's a 0. So we really have a, I don't know if I can draw this very well or not, but it's going to be not that. It's going to be with a negative slope, so it's going to be looking like this. So the point being is that the integrator gives you a minus 20 dB per decade, and this is exact. So this is one case where our approximation is the same as the exact. So again, it's just the same process as before. We take the g of s, evaluate at j omega, and that's what we get.